Hello again. So now we're going to talk a little bit about acids and bases. Just a little quick review on what an acid is, okay? So I'm going to ask you a question and you can pause and, as usual, see if you can figure out the answer to what I'm about to ask. So if I asked you, which of the following is an acid and which is a base out of these species right here? This one and this one. Go ahead and see if you can figure it out. If you said that this right here is the acid and this is the base, you would be correct. And sometimes this is usually represented like that. They usually will say HA and then so forth. They'll have a reaction and then that H, they'll show the H plus to represent the proton that's being given away. And then they'll show H minus to represent where a negative charge to show that a proton was lost, right? So they show that that's a base. But I personally don't like this representation too much. I want to show you a representation which will help you understand acids and bases pretty much wherever you see them, and it's pretty much what has helped me. So let's take any kind of molecule, like let's say an amine, right? So let's say NH2, right? And it undergoes a reaction, an acid-base reaction. Now, if NH2, actually, so NH2 plus, how about OH, right? Now, if NH2 wants to be like an acid, what would happen is you have to give away a proton. An acid is literally just something that gives away a proton. Acid gives proton. Or even better, it donates. That's a good term. It's a proton donor, right? And a base is a proton acceptor. Right? So there's two protons here, because whenever you see a proton given away, if you saw one of my videos, I explained that protons just don't go floating around in space like how electrons do. Especially in acid-base chemistry, usually they're going to be given through the form of hydrogens. Hydrogens are going to split from a molecule, right? And when that hydrogen splits, that hydrogen leaves and then it'll attach another molecule. So this oxygen might be right here, and then it might want that hydrogen to come and attach, right? So that's how the protons are donated. So in any case, one of these has got to go. So that becomes NH. But we're not going to write it here, we're going to write it over there. NH, and then we'll write plus, because if we give away, oh sorry, not plus, we're going to write minus, because if we give away a proton, it means we're increasing the negative charge, right? Because you can always visualize it like this on a number line. Imagine you're right here and you're on a neutral charge. You know you're neutral because here there's no charge associated. It doesn't show that there's a plus or a negative, right? So if you know that it's neutral, you know you're at 0. So if you give away a proton, that means you're going down and you're going to become negative, right? So that's pretty much what that becomes. Then the result becomes that OH will gain the proton. It's the acceptor, right? It's going to go over here. So you can draw an arrow like this. One of these hydrogens is going to go there. And then that's going to end up in HOH or H2O. Right? And there's one mistake that I did here, and you can probably figure out what that is, because H2O is 100% neutral. There's no charge. So what does that mean? That before H2O got the proton, if it's neutral now, this should have been negative, right? And hydroxyl is usually always negative by itself. So that's generally the gist of how an acid-base reaction happens, right? But there might be some instances, like water, for example, which can be an acid and a base. And I'll show you why. Here you have H2O. And H2O may donate one of its protons, and it'll result in OH minus plus H2O. But what happened if we, instead of H2O being the acid, we let's say we gave a proton from another thing, like let's say we had NH2. Let's say we had NH3 here. Okay, NH3 plus. We could easily give a proton from here and donate it on this side. The result would be H3O NH2. That charge would get reduced to a 0, so this has no charge. And this charge would get increased to a plus. So that is what you call hydronium. So that's what you call hydronium, right? And this is just a simple amine with a neutral charge, right? So that's how you would know that water can be both a proton donor and an acceptor. So an acid is literally described as whatever gives away a proton. Okay, so some species you might get fooled. They can both accept one and give one. So the best measure of what is a good acid is pretty much what's the strongest acid. And the strongest acid is whatever results in the most stable conjugate base. What's a conjugate base? Well, in this case, when this amine donated its proton here, the result is whatever happened here when it lost its proton. That is literally what you would call a conjugate base. And then I guess you would be quick in assuming that this is pretty much a conjugate acid, because it was a base that has accepted a proton, and after it's accepted the proton, now it's an acid. Why would it make sense that it's a my mistake, I didn't roll down. Why would it make sense that the conjugate acid is called a conjugate acid? Well, because look, we can take this right here. We can take this hydronium, which is now the conjugate acid, no longer the it's no longer the base. Well, now it has to be an acid. Why? Because we want to get rid of this charge right here. So you can add it over here, and then in the result you'll have H2O over here plus H2O, right? And now, once again, we have a new conjugate. This is a conjugate base because it's accepted with the acid. I mean, it's now it has to accept a proton, and this is a conjugate acid because this base has already accepted a proton. Now it has to give one away. Okay? So that's basically the idea of what conjugate acids are, conjugate bases are, and how acids and protons donate to each other. In another video, we're going to practice with pKa's and pH and all that stuff. But before you do that math, it's good just to visualize what these things are. And you can visually see it if you just look at the structure of H2O. And it's not necessary that you always represent it this way, but you know, it gives you an idea, because you'll see that there's two H's here, right? And you see that over here you have a hydroxyl, right? You'll know that over here, see there's three groups of lone pairs, and oxygen, when it has three groups of lone pairs and one bond, that means that its formal charge is negative, right? So it has too much and it wants to give it away. It has too much electrons, right? And this has no charge because it satisfies the octet and it satisfies the formal charge, which is 6 for oxygen, right? So because of that, this thing right here, when it's an acid-base reaction, it'll give it away to the hydrogen, and you'll give it back over here, and then what will happen is you'll end up having um, this hydrogen here attach to one of these. One of these electrons will form a bond over here, and you can see that represented in the result because you'll see that this now becomes this would have 3 lone pairs now, right? Because one of those lone pairs used to be dedicated to one bond, which is now given away, and the other one, that was the hydroxyl group, but now it has another bond with a hydrogen and 2 lone pairs. So this satisfies the formal charge, so it has no charge at all. This one is electron rich. It goes over the 6 formal charge, because you know in the periodic table when you see oxygen, it goes under the number 6. So this is now electron rich, so it's charged. So you always want to be able to observe these charges to get an idea which acid delivers the proton, which one accepts, and what the conjugate acid and the conjugate base is. So just think about proton donation and proton acception, and that's literally what it is. I don't know if exception is even a word, but I hope that explained all of this.